Hi everybody, this is Tom Cherriams with the FujiNet project, and I wanted to make a video showing an example terminal program written in C/65 for the FujiNet for the Commodore 64 called PETSCIIterm, which allows you to connect to PETSCII BBSs and is tuned specifically for this particular use with a very special feature. That is, it uses the service request pin on the IEC connector to indicate whenever network traffic is present and only do reads whenever network traffic is actually present. This avoids the need to constantly poll and ask the FujiNet, do we have any data? Do we have any data? Do we have any data? And so on. And it makes it possible, as a result, to use the IEC port for applications that you previously could only do over the user port, namely interactive communication. The first part of this video will actually involve demonstrating the program very quickly, while the second part of this video will actually kind of delve into the program and how it works, along with some logic analyzer traces of the bus so you can see how SRQ is actually used. So with that, let's get started. You can load up a copy of PETSCIIterm directly off of our TNFS server here. And once you do, you can run it, and it will immediately talk to your FujiNet and pull down the phone directory that's stored on your FujiNet. FujiNet has a facility, for those that don't know, called app keys, which can be used to store application-specific configuration data separate from the software that you're loading. So even though you're loading a copy of this terminal program off of the network, you have a local copy of the phone directory. And you can add new entries in pretty easily here. We'll go ahead and add one in for Particles BBS as an example. Arrow over, we press the E key to edit, and then we say Particles BBS. And the new URL is, let's see, this uses the FujiNet network URLs, which means protocol followed by address. And so on. So now that's stored. We can come in, we can go back and forth. We can see, okay, that's stored, all good. And of course, you can dial an entry that's in the phone directory, or you can hit O to specify an explicit URL at the bottom of the screen there. We'll go ahead and hit return to dial BBS Retro Academy. And what happens as a result here? You'll see that performance is actually extremely good here. Yes, this is happening over the IEC port, the same port that's being used for the disk drives, for the printers, whatever. It's not happening over the user port. And if we go to something like Gallery, for example, we can see that it actually has really good performance to take and load in individual screens. Doing pretty good, I think. And you can see the keyboard is nice and responsive. We can go and bounce around and do all sorts of stuff in the BBS here, and it works. It does a pretty darn good job here. Let's go to Vintage is the New Old real quick. Pull up some new Vitno. Yay! Oh, a writer's contest. And so on. And so you can see this works extremely well. And because it doesn't need much of the baggage of most communications programs, it's very small, it's very compact. And from a programming perspective, it's very easy to understand. We'll go ahead and end here by hitting a dot to go to exit. Oop. And it looks like yes, we are still debugging IEC timing issues here. So that's normal. We'll go ahead and hit F1 to go back to the dialing directory here. We can either pick something else to run, or we can hit Q to quit and get back to the basic prompt here. Now, for this next bit here, I'm going to pause for just a second to reload the comms program in here for the next part of the demonstration. Those of you who don't want to see the next part of the video, go ahead and shut this off, and thank you very much for watching. To dig down in to see how this works, we'll take and use my workstation here. And over here in the middle, we have a VNC window over to my logic analyzer station, which has a connection to the Commodore 64 that the capture device here on the right is connected to. And we also have a capture output from my Commodore 64, and in the background, we have the source code for PETSCIIterm. The source code is available in a link in the description. You can grab it and follow along if you wish. So if we go ahead and go back in and rerun the program here, what I'm actually going to do now is I will take and restart the trace here. We're going to trace for 1 trillion samples. It really doesn't matter too much how long this goes here, but this will be enough to demonstrate exactly what is going on. So we'll go ahead and start the trace. See, the trace is starting here. We'll go ahead and logically constrain it so it stays in screen. Sure. And we'll go ahead and start the connection here. And you'll start to see some interesting things happening, like, say, for example, the service request starts to go. Okay, great. Now, what happens when we start doing other things here? You'll see that as network activity starts to appear, the SRQ line up top, which is normally not used, is pulsated to indicate that network traffic is available. And this happens precisely because the VIA that this is connected to, or the CIA that this is connected to, only generates an interrupt on an edge trigger. That means every time that the transition for the SRQ line changes, it will generate an interrupt. And we do this nominally every 200 milliseconds or so. And we figure that's sufficient enough to indicate whenever there is network traffic available. But you can see here that this is exactly how this works. We'll go ahead and exit this particular session here. And you'll notice that now it's not so periodically pulsating SRQ, and to try and indicate that the connection has been disconnected here. If we go ahead and hit F1, the connection is closed and everything stops. We can go ahead and stop the connection here, and we'll go ahead and zoom in a little bit to show what's going on here. All we need to do is go into a particular section here to see what's actually happening. We see all sorts of data coming across. And if we zoom into the decoded data, we'll see our PETSCII data being decoded on the bottom right there. But you will also see, as part of the interrupt here, you will see an interrupt trigger for a very short period of time. And this is enough, this is just enough to be able to take and signal to the Commodore 64 that something needs to be dealt with. How is this handled on the source code side? Well, that brings us to our next point here. I'll go ahead and bring the logic analyzer out of the way here. And we'll kind of just go ahead, no problem, and get the capture device out of the way too, because we don't need it at the moment. And we're left with our source code view. This terminal program is basically broken up into two sections. You have the dialing directory and the terminal. But you also have this one particular function here, which we call IH setup. And IH is short for interrupt handler setup. As we can see here, it's referenced in SRQ-.s. And if we go to SRQ.s, we'll see that this routine right here comprises IH setup. It's pretty simple. We have an interrupt handler that's down here, and we basically turn off interrupts for a second, put the new address for IH in place, and then restart the interrupts and then exit right back out. Much the same way, the interrupt handler itself is extremely simple. We have a variable that we define in our C program, which I call trip. It's a tripwire of sorts. And all we're doing when this interrupt happens, when the SRQ happens, because we vectored it into our interrupt handler here, it bounces down and calls this routine every time the SRQ is modulated. So we check the interrupt status register here, and we check for our bit. The 5th bit in the particular register here tells us if the SRQ pin is wiggled or not. If it isn't, then we just go on our merry way and jump to the IRQ handler that's in ROM. Otherwise, we go, oh, okay, we store that value into trip, which sets it to hex n, and then jumps to EA31 again to finish the IRQ handler. EA31 in the Commodore 64 kernel ROM basically does all the timekeeping for things like updating the Jiffy timer, updating the cursor, and just other little odds and ends of housekeeping that need to happen periodically. So one of those is literally, one of those IRQs just happens to be a vertical blank interrupt here. But it illustrates a particular pattern that we can do when you're adding your own IRQ handlers. You check the interrupt status register to see if the interrupt is for you, and if it is, then you do what you need to do. In our case, since IRQs typically need to be as small as humanly possible, it's a good idea to take and just set a variable and go on your merry way. The only other routine here to talk about in much detail here is IHDone, which basically does the inverse of IHSetup and sets the ROM IRQ vector back into place. That's it. You really want to do that because if you don't and you find yourself exiting the program, your system will crash in interesting ways as it tries to jump to code that may or may not be there anymore. So with that, we start looking into the main program. We've gone IHSetup. Directory isn't all that interesting. It's just a good solid way of how to do interactive stuff with ConIO using CC65, and it's responsible for the directory page that you see, that you basically see whenever you first start the program here. And in reality, it basically oscillates between these two states. So right now it's in directory, and it falls out of directory into term, which is the terminal program right here. So there you go. So the interesting part of the program is how the interrupt handler that we initialize at the start of the program gets used inside of term. For that, I'll go ahead and just dot this real quick and get out of here. Okay, now I'll just take and put you to the side again. I keep typing the wrong one. Okay, so that brings us over to, we come back to main, we see a call to term. And if we go to term, this is the meat of the program. Not much going on here. We have some constants set up here that basically you can think of them as like parameters to the open command, basically. Open 2, 12, 2, quotation marks, and the URL that you push in. And then there's the command channel, which I ultimately didn't use in this particular program. But you would use the command channel to do things like send a login and a password for protocols that need it, or set translation modes for protocols that need it, and so on. We have a dial URL, and we have a little flag here that indicates whether or not we're connected or not, and if so, we fall through or we don't. Connect is really simple. You cannot possibly get any simpler than this. All we're really doing is bouncing through, and if we take a look, Oh, command open didn't get pushed into here. Looks like I will have to take and disclose here that I accidentally deleted the latest copy of my code, which meant I lost about an hour's worth of work. But what should actually be here is this. LFN dev san. So basically, you have what is the command, and this is equivalent to an open command in BASIC. And in point of fact, you can rewrite this exact program in BASIC and have it run a bit slower, but still not as bad. And you're not going to lose characters because everything is being buffered at the FujiNet. So we open. Okay, great. And once we're open, we basically oscillate through between a couple of states. We check to see if we're still connected, and then we do input processing and output processing. And I'll show output real quick because it's very straightforward and there's not much really happening here. All we're doing is if we get a hit from the keyboard, we grab the keystroke and we grab as many keystrokes as we can, and then we write the result out to that logical file number that we opened. That's it. That's all we have to do. Now the input is where things get kind of interesting. The input is basically, you'll notice here that all of this is being surrounded by an if statement that checks for whether or not this variable is set to zero or zero or not. If it's set to something other than zero, then we immediately take and read as many characters in as our buffer will allow. And because we're using the kernel IO here, we designate the end of a particular run of characters using the EOI. So the EOI, because we're using the EOI signal to indicate when everything ends, we can simply just take and read in as many characters as we need to. And then we immediately use the kernel routines to take and display them, which for PETSCII, BBSs, and the like, this means that PETSCII characters, color sequences, and everything basically just work as expected. Once everything is displayed, we immediately take and set trip to false, because at this point, at least in theory, the SRQ will have stopped transmitting, will have stopped pulsating because there's no more data waiting in the channel for us. And we can simply take and set trip to false and wait again. Most of the time, you're just going to be sitting here flipping around until trip actually gets activated, and then you'll see, and then you'll process, read the characters, and immediately send them out. Believe it or not, that's it. That's all of it right there. This is all you need to do to implement a terminal program using FujiNet because of the SRQ pin, and because FujiNet is doing all the hard work of grabbing everything off of the network and buffering it in so that you can read it at your leisure. I'm going to go ahead and end the video here because I think I've explained pretty much how this works and shown that this is indeed extremely simple. And I hope that someone will take the source code that I presented here and make something better with it. As always, I'm available on Discord and available on Facebook and other social networks. So you can contact me to ask questions if you want to take and write, your own program like this, or if you want to take and build your own FujiNet. The whole project is open. Please take and jump in and help here. I wrote this in roughly about a day. Wrote and debugged it in roughly about a day. So anyway, I hope this inspires some of you guys. So until next time, have fun.